Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Virial Coefficients from Corresponding States Theory. From the corresponding states theory, we have already seen that the dimensionless intermolecular potential is the same function of a dimensional characteristic distance, that is our dimensionless intermolecular separation distance. That is what we have seen. That means for a fluids of a one class, one particular group of fluids, or let us say fluids, a number of fluids which are obeying van der Waals equation of state, there will be one dimensionless intermolecular potential which would be a kind of universal function of a dimensionless intermolecular separation distance. That is what we have seen. So, analogously, if we apply the same concept of corresponding states theory to virial coefficients and then try to get reduced virial coefficients or dimensionless virial coefficients, what we can have, that is what we are going to see now in this particular lecture. So, intermolecular potential can be written in dimensional form like this. So, this is gamma by epsilon is a universal function of R by sigma, where the epsilon is nothing but the characteristic energy parameter that has been used to make this intermolecular potential gamma as a kind of dimensionless quantity, and then sigma is nothing but a characteristic size parameter, or in general collision diameter for many cases, which has been used to make the intermolecular separation distance R as a kind of dimensionless quantity, that is R by sigma. For that purpose we have used, and then F is a kind of a universal function of reduced intermolecular separation. Okay. So, this is what we have seen, and then according to this corresponding states theory, we have developed several functions for equations of state, like van der Waals equation of state, Redlich-Kwong equation of state, etc. Those things in a reduced coordinates we have already derived, right. Now, if we apply the similar concept to virial equations and then obtain these virial coefficients or dimensionless virial coefficients, what we can get, that is what we are going to see now here. Now, for that purpose, what you do, you take the dimensional form of second virial coefficient, that is B is equals to 2 pi n a integral 0 to infinity 1 minus exponential of minus gamma function of r by kt r square dr. Now, here this is dimensional form. So, in order to make this one as a kind of dimensional form, what we do, we substitute here in place of gamma whatever this epsilon multiplied by universal function of R by sigma. This is what we are going to substitute here. We are not going to get the exact relation like this here, but what we are going to develop, like here in the case of intermolecular potential, we have a generalized expression, that is gamma by epsilon is universal function of R by sigma. Like that we are going to see here reduced virial coefficient could be a kind of universal function of reduced temperature. Okay. So, that is what we are going to see now first, right. So, now when you substitute here, so what will happen then? So, this R, wherever R is there in the right hand side, we are dividing by sigma, so that here R by sigma whole square dr by sigma will be having, so that left hand side also we have to divide by sigma cube, right, so that it will be consistent, and then whatever this 2 pi n a that we are taking to the left hand side, so that what we can have in the left hand side, B by 2 pi n a sigma cube is equals to integral 0 to infinity 1 minus exponential of minus epsilon f of r by sigma divided by kt r by sigma whole square d r by sigma. This is what we get. Now, we know this is nothing but 2 pi n a sigma cube is nothing but second virial coefficient according to what the Hart-Spear model. So, straightforward, this quantity we can take it as a kind of a dimensionless virial coefficient. Further we can make some kind of modifications as well. So, we know that this second virial coefficient is having the units of molar volume, that is centimeter cube per mole, this kind of units it is having. So, what we try to do, we try to write in such kind of form, B dividing by some molar volume quantities, so that we can have a kind of dimensionless second virial coefficient rather than using 2 pi n a sigma cube as a kind of quantity to non-dimensionalize this B, right. So, what we know that sigma is proportional to Vc, right. because Vc, we know that Vc is something like is proportional to sigma cube, something like this, and then this epsilon by k here is nothing but, in this equation epsilon by k is nothing but the critical temperature. So that we can write this left hand side B by Vc is equals to integral 0 to infinity 1 minus exponential of minus Tc by T function of r by sigma multiplied by r by sigma whole square dr by sigma. This is what we can write it. Now, what we can understand here, so now we have here B by Bc, that we can write it as a kind of dimensionless the second virial coefficient. We are not taking all those constants, we are not doing exact derivations kind of thing, we are trying to find out the form. So, now we can see here, so left hand side we can have this whatever B by 2 pi Na sigma cube, we can equivalently write B by Vc because of this relation, right. And okay, and then right hand side what we have, this Tc, now in place of epsilon by k, if I write Tc, then Tc by T, so T by Tc is coming, so that this T by Tc is coming in the exponential. So, that is nothing but reduced temperature, and rest everything are in a kind of some function of r by sigma and all those kind of things are there. So, analogous to this dimensionless intermolecular potential, according to corresponding theory that we have, that gamma by epsilon is equals to universal function of r by sigma. So, analogous to that one, we can have a kind of a dimensionless reduced second virial coefficient as a kind of universal function of reduced temperature for a given class of fluids. Since it is this this B is for only virial equation of state, so this universal function is also for only the fluids that are obeying virial equation of state. So, we can say Fb is nothing but universal function of a reduced temperature. What we know, B is a function of only temperature, right. If you write it in dimensional form, this is what we have already seen. It is not function of pressure or density, etc. So, if you write in a reduced form, that is B by Vc, then you can be having some kind of a reduced function of a reduced temperature. You can have a kind of universal function of a reduced temperature T by Tc. So, it is possible that if we apply this corresponding states theory to the virial coefficients, so then these virial coefficients we can write as a kind of a some kind of universal function of reduced temperature. So, what are these functions that we have to derive, or we have to see from the experimental information, whatever the possible way. So, obviously, these are the derivations are not possible, they are obtained from the experimental data by doing so many of by doing a kind of curve fitting kind of things. So, those things we are going to see now. So, this equation 2, whatever this B by Vc is nothing but Fb of T by Tc indicates that the reduced second virial coefficient is a generalized function of reduced temperature. This function can either be determined by simply specifying the universal potential function, what is that gamma by epsilon, and integrating this one as shown in that expression B is equals to 2 pi Na integral 0 to infinity 1 minus exponential of minus gamma by kT r square dr. In this equation you can substitute whatever that gamma, and then simply you can do the required integration, so that you can find out what is that universal function of reduced temperature, okay, because temperature we are not substituting here, or by direct correlation of experimental data for second virial coefficient. Whatever the second virial coefficient information is there, that experimentally that you obtain, so that you can plot for a reduced temperature. Let us say B by Vc may be having something this kind of trend, something like this. So, maybe here you may be having 0, and then here minus 1, minus 2, minus 5, something like this for different TR reduced temperature, you can get a curve like this. So, this is if you have this information from experimental source, then that way also you can do the curve fitting for this B by Vc versus TR information that is obtained by experiments, and then obtain such what is that universal function, that can also be done. So, for example, McGlashan and Potter, what they have done, they have plotted reduced coordinates experimentally and determined the second virial coefficient for the a few simple symmetrically simple molecules like methane, argon, krypton, xenon, and then data for 4 gases are well correlated by their correlation, empirical correlation. So, what they have for these 4 gases over the wide range of reduced temperature, they have conducted the experiments and then found second virial coefficients. Those second virial coefficients, then they have converted in terms of a dimensionless form by dividing this B with a critical volume Vc, right. Then whatever the B by Vc versus Tr or T by Tc information is there, that they have done a kind of correlation or experimental empirical correlation fitting they have done. So, then they got this correlation here. Okay. So, obviously it is established for pure components because they have taken these 4 components as a kind of pure components, but however by using the results of statistical mechanics and molecular theory of corresponding states, this can also be extended to the mixtures by using appropriate appropriate Tc and Vc for mixtures. Though this correlation is developed only for pure gases, but appropriate Vc and Tc if you can have for a mixture either by statistical mechanics results or by molecular theory of corresponding states, then it has been found that this equation can also be extended for the mixtures and then validity is sufficiently satisfactory. So, now if you wanted to calculate B from that McGlashan and Potter correlation, what you need? You need Vc and Tc of pure components, right, because in the right hand side you have T by Tc, in the left hand side you have B by Vc. So, Vc you need, Tc you need, and then at required temperature you can calculate that B information for a pure components, right. But if you need to know the second virial coefficient for the mixture, so then B mixture can be taken as a sigma I is equals to 1 to m, sigma j is equals to 1 to m, yi, yj, bij. This is this expression you can use for finding out the B mixture or the virial coefficient for the mixture of m components, for which if you know the second virial coefficient as a kind of pure form. In the pure form, if you know B11, B22, B33 and so on, so BMM, all those things, then using this expression you can obtain the B mixture or the second virial coefficient for the mixture, right. That is possible for different composition of these gaseous mixture. But in this expression we also have a kind of cases, if I is not equals to j, then we have Bij. So, that is cross virial coefficient we have to find out. So, again cross virial coefficient again you can find out using the same McGlashan and Potter correlation, but what you have to use? You have to use appropriate Vcij and Tcij if you wanted to calculate Bij, and then without Bij you cannot use this equation, right. So, that Bij if you wanted to calculate, Tcij, Vcij you have to find appropriately, because if it is Bii or Bjj, so these are for the pure components, critical temperature, molar volume are available. Okay. So, to calculate cross virial coefficient Bij, again the same equation we can use, but Vcij and Tcij we have to use the appropriate one. And then from semi empirical combining rules, we know that sigma ij is nothing but the arithmetic average of sigma I and then sigma j. So, that is sigma I plus sigma j by 2 is sigma ij. So, and then we also know the characteristic energy that has been used for the non-dimensionalizing the intermolecular potential for 2 different molecules, ij molecules, then that is epsilon ij is nothing but square root of epsilon I, epsilon j. These are the mixing rules kind of, or combining rules kind of thing. And then since we know that Vc is proportional to sigma cube, then Vcij we can write it as 1 by 8 cube root of Vci plus cube root of Vcj and then to the power 3. This is how we can write. So, you can use this equation for Vcij. And then Tcij is nothing but simply square root of Tci, Tcj. right, and this is a kind of upper limit. It gives kind of upper limit of TCij, right. However, this upper limit TCij if you use, then also you get a kind of satisfactorily reliable results for a cross virial coefficients Bij, right. Now, this temperature given by equation 8 is upper limit for TCij, and then that equation whatever the Maclaurin and Porter correlation is there, it gives good representation of second virial coefficient for small non-polar molecules, but for large molecules this equation is not satisfactory. Okay. So, in order to overcome that, what they have done, Maclaurin et al., they proposed following correlation, which is nothing but the modification of the existing correlation, that the equation number 3, that is Maclaurin and Porter correlation. In the right hand side they have added one more term. So, this is the another term for the larger molecules. Up to this point it is same as equation number 3 that we have been using for small non-polar molecules, simple small non-polar molecules. But if molecules are large, so then they have proposed a kind of a correlation by adding this subtracting this particular term, where n is nothing but the it indicates the number of carbon atoms that are present in the molecules. Let us say for CH4 n is equals to 1, right, and this correlation is valid for molecules having up to 8 carbon atoms, that is n is equals to 8, it is valid up to n is equals to 8 level. And then experimental critical values for alpha olefins are not highly accurate in general. So, for that they have done what they have done, they have also provided correlations for this critical volumes, that is Vc. Further, because the critical values for alpha olefins have not been measured for n greater than 4, they propose this Vc to be calculated using this expression. Olefins for n less than or equals to 4, this critical volume informations are available, but if n greater than 4, then whatever the available critical volume information is there, that is not reliable. Reliable in the sense the reproducibility is not there, or different literatures are reporting different values, kind of ambiguities are there. Under such conditions, for n greater than 1, the same authors have also proposed a correlation for Vc as function of n. N stands for the number of carbon atoms present in the molecule. Okay. That is given by this equation. Vc is 25.07 plus 50.38 n plus 0.479 n square. Now, by incorporating correction to equation number 3, the new equation whatever this equation number 9 is there, it gives a very good matching with experimental Bs of pure components of large molecules as well. The previous correlation anyway it gives a good matching with experimental results for small non-polar molecules, but by making this addition, this correction, they have found that their results are matching better with the experimental results, even for large molecules. But for mixtures, one problem is that we have to use the mixing rules for n as well, and then for n they have they assume that the arithmetic average of n1 n2 can be taken, that is n12 is nothing but n1 plus n2 by 2, that is what they proposed. Okay. Now, we take another correlation, Pidger and Sonopoulos's correlation. So, we already know that Pidger has suggested eccentric factor for non-spherical molecules. Non-spherical molecules are nothing but the molecules, the force field around which are not symmetric, then we can call them as a kind of non-symmetric molecules, right. For them, the eccentric factor has been defined. So, actually this is defined based on a kind of experimental results, that for simple small molecules, that is for simple small molecules, what happens, when temperature or when reduced temperature is 0.7 or when T by Tc is 0.7, then Ps by Pc, that is the saturation pressure by critical pressure, has to be 1 by 10 or has to be 0.1, right. That is true for a simple spherical molecules, but if the molecule is not spherical, then obviously that Ps by Pc will not be 0.1 when T by Tc is equals to 0.7 for non-spherical molecules. So, that information has been taken as a kind of basis for defining this as eccentric factor, and then they provided this omega is equals to minus log of Ps by Pc at T by Tc is equals to 0.7 minus 1. So, obviously for simple spherical molecules, when T by Tc is equals to 0.7, then Ps by Pc is nothing but 0.1. So, if you substitute 0.1, then omega would become 0. This is also we have seen, right. If it is not a spherical molecule, so obviously at T by Tc is equals to 0.7, Ps by Pc will not be 0.1 for that non-spherical molecule. So, that information will be coming into the picture as a kind of eccentric factor omega here, right. So, now when applied to second virial coefficient, the extended theory of corresponding states assumes that for all fluids in the same class we will be having this form B by Na sigma cube is equals to some universal function of f omega of kT divided by epsilon. This is what we can see from the extended theory of corresponding states in a similar way as we have done, like in the previous case. What we have taken this gamma by epsilon is equals to some universal function of r by sigma. This is what we have taken, right. So, this is coming from the principles of corresponding states theory, right. But this is developed for only the cases where the equations of states are having only two constant. For those kind of things only it is valid, for then only you can find out this universal function. But it has been found that is not possible for the bigger molecules, non-spherical bigger molecules. Then extended theory of corresponding states has come into the picture through this factor, and then this omega is coming as a kind of a third parameter, right. Let us say van der Waals equation of state, you have A and B constants only. This A and B constants may be applied can be obtained by applying this principle here, right. But if you have Penn-Robinson equation, so then there is a kind of alpha as function of t, and that alpha is function of t, which is again function of omega eccentric factor. So, that third parameter is coming into the picture. So, that can be obtained from here like this. So, the same extended corresponding theory. So, this is known as extended corresponding theory. We are introducing additional parameter in addition to these two constant parameters in general found in cubic states of cubic equations of states. So, now we have a kind of additional parameter omega. When we brought this additional parameter, it also makes sure that this theory also applicable for the other non-spherical bigger molecules in terms of having additional parameter omega, right. If you apply the same concept here, like in the previous case where we have applied for this b is equals to 2 pi Na integral 0 to infinity 1 minus exponential of minus gamma by kT r square dr, this information we had, right. So, now similar way if you apply here again and then incorporate this omega information here, so then we can get this kind of form, right. So, here again we know this epsilon by k is nothing but the characteristic energy. So, it is having the temperature units. So, the Tc will come into the picture, and then sigma is nothing but the characteristic molecular size, right. And then this Fw depends on the eccentric factor, and for any given omega it applies to all substance that having same omega, right. And then further this sigma cube is proportional to Vc, and then epsilon by k is proportional to Tc. So, applying them here we can write further Vc is nothing but Zc Rtc by Pc, right. So, because now here in Zc is nothing but Z0 plus some function of Z1. We have seen this function f is now function of eccentric factor. This is what we have seen. So, because this whatever this compressibility factor is there, that is again changing from one group of fluid to the other group of fluids. So, this is for the simple spherical molecules, and then additionally this is coming for a things where non-sphericity is there, right. So, now ZC has to come into the picture. So, then for that purpose Vc is replaced by the ZC RTC by PC, because we know ZC is nothing but PC Vc by RTC. So, and then ZC is function of omega only, that we know through this relation. Okay. It is not function of any thing like reduced temperature etc. It is function of only omega here. Okay. So, then we can say ZC can be absorbed in Fw, right. So, that omega can also be absorbed in whatever that Jc as function of omega, whatever that information is there. So, that can be absorbed in Fw. So, that we can write the same equation, whatever B by Na sigma cube is equals to Fw kT by epsilon, that we can write it as B Pc by RTC is equals to F omega T by Tc. F omega T by Tc we can write. So, now what we have previously, when we use the 2 parameter corresponding states theory, then we have B by Vc is some kind of a universal function of T by Tc, right. But now here when we use the extended extended theory of corresponding states, then we have this B is non-dimensionalized using RTC by PC, that is P, that is B Pc by RTC is a universal function of T by Tc or reduced temperature, that is what we see. So, now for bigger molecules which are non-spherical, whatever the correlation that we are going to see, they will not be of the form B by Vc form, rather they will be of form B Pc by RTC is equals to some universal function of reduced temperatures. So, those things we see now one by one. So, Schreiber and Pitzer proposed a correlation of form as indicated by equation 11. So, equation 11 what we have, this B Pc by RTC is some function of T by Tc or Tr. Okay. So, now that way if you write B Pc by RTC Zc is equals to C1 plus C2 by Tr plus C3 by Tr square plus C4 by Tr power 6. This is the correlation they proposed in this particular form for the non-spherical molecules, where Tr is nothing but the reduced temperature, that is T by Tc, and Zc is nothing but compressibility factor at critical point, and it is approximated by Zc is equals to 0.291 minus 0.08 omega. Okay. Zc is a function of omega. Now, in this equation what we have? We have 4 constants C1, C2, C3, C4, right. So, what are they? They are dependent, they are again dependent on omega, and then how are they dependent? They are dependent as Ci is equals to Ci comma naught plus omega Ci comma 1. And for non-polar and slightly polar fluids, these coefficients are provided like this. If I is equals to 1, then this is nothing but C1 comma 0, this is C1 comma 1. If I is equals to 2, then it is C2 comma 0, this is C2 comma 1, and then if I is equals to 3, then this is C3 comma 0, and then this is C3 comma 1, like that C4 comma 0, C4 comma 1, and then let us say C should be taken as, for the first case C1 should be C1 comma 0 plus omega C1 comma 1, and then C2 is equals to C2 comma 0 plus omega C2 comma 1, like that we have to find out C3 and C4 and then substitute them here, okay, in order to get this B value from this equation number 12. So, further next Sonopoulous gave another correlation for second virial coefficient in the form Bpc by Rtc is equals to some function f naught of Tr plus omega some function f1 of Tr or T by Tc, that is what he has given. And then what are these f naught and f1? They are nothing but again function of Tr as given by this equation number 14 and then 15, right. So, simply for this case what you have to find out? You have to find out what is the Tr, substitute Tr in this equation number 14 and 15 to get f naught and f1, and then substitute that f naught f1 along with this omega value in this equation number 13 to get BPC by RTC, and from there you can get the B value, right. So, these equations 13 to 15 provide a good correlation for second virial coefficients of fluids having spherically symmetric molecules. Spherically symmetric molecules, already several good correlations are there. And what is the advantage? The advantage or the purpose of applying the extended theory of corresponding states to get a better quality or better improved virial coefficient for non-spherical molecules also, better improved in the sense having a better agreement with the experimental results. So, in order to fulfill that requirement, what Xenopolus have done, they have modified this correlation given by equation number 13 by adding additional term here like this one, F2 function of T by Tc. So, this is nothing but equation number 13. If you use only up to this part, this is good for spherically symmetric molecules, but if you wanted to apply for the non-polar for a case of polar and non-spherical particles or molecules, then you have to add a kind of additional function to make a kind of adjustment, so that experimental validity should be good. Okay. And then this F2 is nothing but A by Tr power 6 minus B by Tr power 8. Again this A and B are the constants which cannot be generalized easily, but however for polar fluids that do not hydrogen bond, these guys Xenopolus found this B as a kind of 0, but for the case of A, separate relations are provided based on the type of molecule of consideration, right. So, now what we have, let us say if we have ketones, aldehydes, alkyl nitriles, ethers and carboxylic acid esters etc., then Xenopolus have proposed correlation for A as A is equals to minus 2.14 into 10 power minus 4 mu r minus 4.308 multiplied by 10 power minus 21 mu r power 8. Mu r is nothing but reduced dipole moment, mu is nothing but a dipole moment, and then mu r is nothing but a reduced dipole moment, right. So, similarly for alkyl aldehydes, mercaptans, sulfides and disulfides also they have proposed a correlation for A as minus 2.188 multiplied by 10 power minus 11 mu r power 4 minus 7.831 into 10 power minus 21 mu r power 8. Here mu r is given as 0.9869 into 10 power 5 mu square Pc by Tc square. Okay. So, this mu here in this equation 20 is nothing but dipole moment which is in dBi, and then Pc is in is critical pressure which should be in bar, and then Tc is nothing but critical temperature that should be taken in Kelvin in order to get this reduced dipole moment mu r. Once you have this mu r information, then A and B, then A constants you can find out depending on the nature of the fluid of consideration, okay, and then that can be used in equation number 14 to get the required B information. For water, A is recommended as minus 0.0109. And then it is difficult to correlate second virial coefficients of polar and hydrogen bonded fluids in general, because first one is that experimental results inadequate information on their intermolecular forces, obviously because of inadequate information on their intermolecular forces, and also experimental results on second virial coefficient of such polar and hydrogen bonded fluids is very scarce. That is the reason it is difficult to find out second virial coefficient for polar and hydrogen bonded fluids. Now, third virial coefficient from corresponding states theory, if you apply the corresponding states theory, then similarly we can obtain the dimensionless third virial coefficient as well. We know that reliable experimental data are very rare for third virial coefficients of pure gases and extremely rare for a gaseous mixture, that we already know. So, having experimental information very scarce, it is also difficult to have a more number of correlations, right. Obviously, we will have a very few correlations. Okay. So, for that, for non-polar gases, reduced third virial coefficient, that is CR, is given as C Pc square divided by R square Tc square is equals to F naught function of Tr plus omega F1 function of Tr. So, here C is dimensional third virial coefficient and Cr is nothing but a reduced or dimensionless third virial coefficient. Okay. So, this F1, F2 are given. Similarly, for polar gases also this Cr they have proposed as this thing, Cr is equals to F naught function of Tr plus omega F1 function of Tr plus additionally they have this reduced dipole moment for the case of polar gases are the terms associated with the reduced dipole moment, right, that is mu r power x function of f of 2, that is mu r power x F2 function of reduced temperature Tr, right. So, this x is a component dependent, a substance dependent empirical constant. So, where F naught, F1 are regressed have been obtained from the experimental data by regression analysis, then F naught is given by this correlation which is function of Tr. Similarly, F1 is also given by this equation number 24 and mu r is nothing but the reduced dipole moment which is same as previously we have seen, that is 0.9869 into 10 power 5 mu square Pc by Tc square. Then x is empirical substance dependent constant, it depends on the substance. So, we cannot have a one constant value, these informations are available in the literature. So, now before concluding this lecture what we do, we will also see a few virial coefficients of quantum gases like hydrogen, helium and neon. For these gases good experimental results are available, thus generalized correlations are not necessary, because these correlations or the reliable experimental relations are directly correlated to the dimensional form of second virial coefficient, that is B, and then dimensional form of third virial coefficient, that is C, straightforward without making it in a reduced form or dimensionless form, right. So, for H2 Goodwin and co-workers established the following correlation for the second virial coefficient sigma Bi x power 2i minus 1 by 4, I is varying from 1 to 4 and then B1, B2, B3, B4 are given, x is given as 109.83 by T, T has to be in Kelvin, B1 is given, B2 is given, B3 is given, B4 is given. And then this correlation for B is valid in the range of temperature 15 to 423 Kelvin, and then mean deviation from experimental data is very small, that is plus or minus 0.066 centimeter cube per mole. So, such good is correlation that deviation from experimental result is almost like plus or minus less than plus or minus 0.066 centimeter cube per mole. That is the reason these correlations are not required in a reduced form. Third virial coefficient again given by Goodwin and co-workers as C is equals to 1310.5 square root of x multiplied by 1 plus 2.1486 x cube multiplied by 1 minus exponential of 1 minus x power minus 3. Okay. And this third virial coefficient is valid again in the same range of temperature 24 to 423 Kelvin, and deviation from experimental result is plus or minus 17.4 centimeter power 6 by mole square. Similarly, for helium second virial coefficient is given by this expression as function of temperature, and then third virial coefficient is given by this expression as function of temperature again, and then temperature here in these two correlation is given in Kelvin, which is valid between 300 to 1000 Kelvin. Likewise, for neon tabulated information is available, so one need not to go for a kind of correlations. Now, what we do, we take an example how to make use of these correlations in order to get virial coefficient for pure substances as well as the virial coefficient for cross or as well as the cross virial coefficient. So, how to make use this equation, that is what we see now, okay, by taking an example problem. consider a gaseous mixture of 1 mole containing 1 mole percent of CO2 and 99 mole percent of H2. Out of 1 mole, 99% is H2 and then 1% is CO2 on mole basis, right. Assume that the mixture obeys virial equation of state. The mixture is compressed isothermally to 60 bar at minus 100 degrees centigrade, so that to check whether the precipitation of CO2 occurs or not. That is, the process is occurring, but we are not going to check in this problem whether precipitation is occurring or not. But for this case, we will be finding out the second virial coefficient of both the components and cross coefficients as well. What is the compressibility factor and molar volume of the mixture, that is also we are going to find out. Okay. So, we have to use correlation to obtain this second virial coefficient, because intermolecular potential information is not at all given, only component information is given, and then how much what is the composition of that mixture is given. Two components are given and their mole percentage composition is given. So, from that information we cannot obtain second virial coefficient. So, obviously for these components CO2 and H2, critical temperature, pressure are in general available in any standard thermodynamics book. So, we can use that information and then use the correlation that we have discussed to get those virial coefficients, okay, for both pure components as well as for a cross virial coefficient. So, we need the data. So, data is also given for CO2 as well as H2, Tc, Pc, Vc and omega are given for both the component. So, this is more than sufficient to find out what is BCO2 and then what is BH2, similarly what is BCO2 H2 for the pure as well as the cross coefficient. This information is sufficient to get, so that is what we are going to do. So, for first case, Scher and Pidgeot correlation we will be using in order to get the second virial coefficient of a CO2 gas, right. So, that is, this correlation is nothing but BPC by RTC ZC is equals to C1 plus C2 by TR plus C3 by TR square plus C4 by TR power 6, and then for CO2 omega is given as 0.239. So, ZC is defined as 0.291 minus 0.08 omega according to this correlation. So, when you substitute omega here 0.2719, you will get it as a compressibility factor. Omega is given anyway, and then TR is nothing but T by Tc. T is mentioned as 173 Kelvin or minus 100 degrees centigrade, okay, and Tc for this CO2 is given. So, you will get TR as 0.5689. So, C1 we have to find out as C1 comma 0 plus omega C1 comma 1. So, C1 comma 0, C1 comma 1, these coefficients are available in the tabulated form in the correlation. So, that we are using. So, C1 you get this one, likewise C2 you get this value, C3 you will get this value and C4 you will get this value. TR already you got 0.5689. So, this information if you substitute in this correlation, then you will get BCO2 PC RTC ZC is nothing but minus 5.3145, right. From here BCO2 you can find it out minus 495.0052 centimeter cube per mole. So, for the CO2 second virial coefficient for a pure CO2 is obtained, that is BCO2 we got it, right. So, now BH2 we have to get, or pure hydrogen what is BH2, the second virial coefficient for pure H2, that is what we have to get. So, for quantum gases we have the Goodwin and co-workers correlations, so that we can use for H2, right. So, Goodwin and co-workers correlation in expanded form, BH2 you can write it as B1 x power 1 by 4 plus B2 x power 3 by 4 plus B3 x power 5 by 4 plus B4 x power 7 by 4, and then x is nothing but 109.83 divided by T in Kelvin. So, B1, B2, B3, B4 are available according to these correlations. So, only thing that x you have to find out, that is 109.83 divided by 173. So, and substitute here, then BH2 you will get it as 8.82 8.8269 centimeter cube per mole as a kind of a BH2, that is for the pure component, pure hydrogen. Okay. So, B11, B22 we obtained. So, B12 we have to obtain. So, B12 here in the sense BCO2 H2. So, that we have to do. So, for that purpose what we do? We use another correlation. We use Maclaurin correlation. We are using different correlations because within one problem we can use almost all correlations that are available for symmetrically spherical molecules, non-spherical molecules as well as the quantum gases. All three cases are covered in one single problem. So, Maclaurin correlation we know it as B12 by B12 is equals to 0.43 minus 0.886 T by Tc12 power minus 1 minus 0.694 T by Tc12 power minus 2. So, now this Tc12 is nothing but square root of Tc1 Tc2, right. So, that Tc1 Tc2 are given as 304.1 and 33 respectively, you substitute here. So, then Tc12 you will be getting 100.1763, right. So, now we also need V12. V12 is given as 1 by 8 multiplied by cube root of Vc1 plus cube root of Vc2 to the power 3. So, then when you substitute this Vc1, Vc2 given information here and then simplify, then Vc12 you will get 78.163 centimeter cube per mole. Then Tr12 is nothing but T by Tc12, that you get approximately 1.73, and then B12 by Vc12 if you substitute in Maclaurin correlation you will get minus 0.3140, thus B12 that is BH2CO2 is nothing but minus 24.5462 centimeter cube per mole. So, this is how we can make use of these correlations, so that to get second virial coefficient without much information from the problem statement. Only thing that you need to have a kind of information about their reduced temperature, reduced pressure, or indirectly you need to have only the information about the critical temperature. Okay. Once you have the critical temperature and critical pressure, so then you can have a kind of reduced temperature, that is the temperature at which you wanted to find out the virial coefficient, that divided by the critical temperature, then that will give the reduced temperature. So, any of these correlation appropriately depending on the nature of the molecule you can use and then get these second virial coefficients. And now coming to the compressibility factor, and then molar volume of the mixture is also need to be found. It is mentioned that CO2 is very small, it is only 1%, 99% is H2 is there. So, that means we can say whatever the Z mixture is there, that is approximately ZH2 we can say. So, obviously whatever the V H2 is there, that we can say V mixture. So, then VH2 is nothing but ZH2 RT by P, and then so but this ZH2 we have to find out. ZH2 is nothing but 1 plus P BH2 by RT according to virial equation of state, right. So, now P is given as 60 bar, T is given as minus 100 degree centigrade, and then BH2 just now we found it as 8.8 something. So, that if you substitute here ZH2 you are getting 1.0367. So, VH2 is nothing but V mixture. So, that is nothing but ZH2 multiplied by RT by P, that if you substitute ZH2 as 1.0367 and then T as 173 and P as 60 bar, then you will get it as 248.52 centimeter cube per mole. Okay. So, coming to the references for this lecture, the Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prosnit et al., then Chemical, Biochemical and Engineering Thermodynamics by Sandler, and then Introduction to Chemical Engineering Thermodynamics by Smith et al. But this entire lecture including the example problems are taken from this reference book. Thank you.